Hi guys, welcome to the what. So today we will do MATLAB simulations on non-isolating open loop DC to DC boost converter. So let's start. So what is an open loop non-isolating boost converter? So boost converter is a DC to DC converter which will help us to step up the supply voltage. So the basic principle here is we will charge our inductor for a few seconds or for a few microseconds, and we will use that as an additional battery to our DC input source. So if, for example, here we have DC input, that is Vn, for example, this is 5 volts, and here we have L1 as our inductor. Here we have a MOSFET switch which will be operated on our triggering device. We have a diode. We have a capacitor for smoothing the output, and we have a load, right? So first what will happen? For example, this MOSFET switch has only two functions. First one is on, the second one is off, right? So for example, let's start with on function first. So this switch is on, so that means this whole thing is short circuited. So here we have 5 volts, so the current will pass from L1 inductor and will go back to the battery. So this will charge the L1 inductor with the polarity plus and minus while charging. So after a few milliseconds, we will turn off that particular switch. So whenever if we turn off this particular switch, so then what we will have? We will have the current will flow from this diode. It will not go into the capacitor. A small amount of current that is known as charging current will go in the capacitor, and the main current will flow through the load, and then it will move back to the 5 volt DC input, right? So now what will happen? So this inductor, earlier the polarity was plus and minus, but now the polarity will be opposite. So as we know that if this polarity is opposite, this whole thing will behave as a battery. So here we have plus and minus, here we have plus and minus. So we can say that we have connected two batteries in series. So if we connect two batteries in series, our current will be constant, but the voltage will add up. So this 5 volts plus whatever the voltage will be accumulated here. So we can say that the final voltage that we are getting as output will be 5 volts plus the voltage of this inductor. So that is increased voltage, right? So we will see it's working. We will draw and we will simulate the whole thing on MATLAB. So first of all, what components do we need? So the first and foremost, the most important one, that is the DC voltage source. Then we will have this RLC series branch, and then we can convert this branch to make it inductor, capacitor, or resistor, right? We have voltage and current measurements. We have diode. We have MOSFET switch. We can use IGBT as well. We have sine wave generator. We have gain for multiplying. We have constant. We have a comparator. We have scope for visualizing our waveforms. We have display. We have power GUI. So power GUI is very important. We have to have this in each and every MATLAB simulation. And then we need ground and one add block. So normally here, as we can see here, it is a square wave driving switch. So in MATLAB, we have already a provision of a pulse generator. So it will look like something like this. So here we can directly give these pulses to our MOSFET or IGBT, right? But right now today we will not use this particular pulse generator. We will create this type of pulses using sine wave generator, constants, comparator, etc. Right? So this is very simple to use a pulse generator, but today we will create this and then we will power our boost converter. So let's go. Okay. So these were the components that we need. So let's start. So first one is DC voltage source. So now here we have two types of DC voltage source. Let me show you. So the first one is this one, the blue one, and the other one is the black one. So we will use this black one. So add. The second one is RLC series branch, right? So we'll write RLC series RLC. Not load, we can use series RLC branch, right? Then we will go for voltage measurement, current measurements. We will go for diode. Diode, we also have diode in multiple design. So we will use this one, this particular diode. This is a power diode. Then we will use a MOSFET. Then we will use a sine wave generator. Then we have gain. Then we have constant. We have comparator. Now this comparator we need to take. There are different types of comparator. Let me show you. So this is compared to a constant, compared to 0, something like that, right? So we can take anyone with 2 inputs and 1 output. Logical operator is also there. Relational operator, yes. We will take this one for comparison. Right. Then scope display. Scope display. Power GUI. And then we have ground. Now here also we have different types of ground. So this one, electrical specialized power systems, fundamental block elements, we will use this one. And then we have add block. So add, I guess that's it. So let's start. Let's keep this aside. Yeah, we have diode, MOSFET. We'll just disable the measurement port for the MOSFET. So as we can see, we have one G, D, and S, right? So G is the gate pulse. This MOSFET is already has an inbuilt diode for reverse flowing of current. So we can see this diode here. This is good for us. Display. So let's start. So here we have our DC voltage source. Then we will convert this RLC branch into inductor L with a value of 870 microhenry. because this is the value we are using for designing. So 870 micro Henry. So here we have our inductor. We will put a current measurement device here to measure our current inductor. Then here it would be MOSFET. Right. Then we will have our diode here for the prevention of reverse current flowing. Then we will convert this RLC branch, we will convert this into a capacitor of, according to our design, it is 2034 microfarad, and we will use resistance as well, 10 ohms, that is enough, right? So, and we will need one more current device here for the measurement of the load current, right? Here we have a measurement for the DC voltage. Here we'll measure the output voltage. We have scope here. So let's connect everything. Let's keep two inputs so that we can compare our input with output. Let's keep ground here. Okay, so our basic circuit for boost converter is ready. Now we need to do something about this gate pulses. So now we will generate these gate pulses. So we will put a sine wave. We will have a constant block. We will have a gain block. So here what we are doing, basically we are comparing a constant with a sine wave, and according to that we are getting our values, right? So here is addition block. Here is the comparator one. Here one more scope. So now first let's observe the sine wave. So sine type will be time based. Use simulation time. We can use external signal as well, but here we are using simulation time. Amplitude is 1. It will start from 0, it will go to +1. Let's see. Biased, we are putting 0 bias. Frequency is 1 radian per second. So here they have given us that this frequency would be 2 into pi into f into sample time, right? So here just we need to do 2 into pi into whatever hertz we need to convert the whole thing into radian, right? So frequency we are keeping 5,000, right? Okay, let's not take this sine wave, for instance. Let's take triangular wave generator. Yeah, this would be better because we will use sine wave in closed loop operation. Here we will just change this. We are taking a triangular wave generator, right? So in a triangular wave generator, what do we have? We have frequency, that is how many hertz. So normally we keep frequency in kilohertz when we use boost converter for smooth operation. So let's keep 10,000 hertz or 10 kilohertz. Okay, right. So let's see that how it will look like. We will simulate for 3 cycles, 3 normal cycles, or we can say 3 power cycles. So here let's see our triangular frequency, triangular wave. So here we can see that it is going from 0 to 1, then it is coming back to here, and here, right? So it will move from 0 to 1 and coming to -1 as well. So now what we need to do, we are pushing this whole thing in only positive side, right? So we will push this particular thing in positive side. I'll just let you know the reason. First, let's do it. So for pushing this whole wave upwards, we need to add 0.5. So that's why I have a constant here. So we have this. We have a constant we need to push. So we are adding 0.5. Now let's see the output. So now, as we can see, it will start from, okay, so let's keep here 1. I forgot that the amplitude was 1. So let's put the amplitude as 1. So now we can see everything is greater than 0. Waveforms will remain same. So now it will go from 1 to 2 to 0, right? Okay, so we'll have this. I usually put a gain block because I see here what we are dealing with. We are dealing with 0 and 2. Our range is from 0 to 2. I personally love to work with 0 and 1 only. That's it. So I'll put a gain of 0.5. This will divide the whole thing. So now we can see, now here we can put 0.5. So we can see that now it will go from 0 to 1. See, 0 to 1, right? Everything will remain same, right? It will start from 0.5, it will go to 1, then it will go to 0. This is the one that we want. Okay, so now let's compare it. Let's put this thing here. We need one more comparator. So now we have this, we are comparing this. We are putting 0.5 deliberately. I'll show you why. So now let's take a multiplexer. So what is this multiplexer? Basically, it will multiply two signals and it will generate a common signal, right? So what we need to see, we are multiplying our triangular wave as well as our constant wave, and here what we will do, we will have the layout of 2, where it would be 2, right? So on the first one, we will see the comparison, and the second one, we will see the actual gate pulses. So let's see. So here, as we can see, that, see, so it will start from 0, it will go till 1, and now we have this constant which was going, which is 0.5. So now this is comparing the whole thing, right? So now we are seeing that to all the parts where this triangular wave is smaller than this constant, we are getting a high pulse. And in all the parts where this triangular wave is greater than this constant, we are getting a low part. But we actually want reciprocal of this. So we will just change the sign. Why we are keeping the reciprocal? Because whenever you will change this, according to your output should change. So the higher value of your constant, your output should be higher, not the ulta of that. So here now we saw this, that if we will increase this particular thing, wait, now we will see as we increase this, we will have a large output. For example, let's see, here I am putting 0.5 as of now. So for 0.5, that means we have 50% duty cycle. This is the whole duty. So here we will put 0.75 for the comparison. Now we will see, we will have a greater part where we are having positive cycle C, right? So our constant will go up. We will have a large positive and a small one as 0. So according to this pulses, the width of this pulses, we can control the output of our DC to DC boost converter, right? So here we are getting correct gate pulses. Let me keep this as 0.5 as of now, right? And the gate pulses will be this one. Okay. Now let's take one more scope. Scope 1 will be given from the input current, and scope, the second part of this thing, will be the output current. Okay, so I guess we are done here. Let me save this. So let's go through everything. This is a DC to DC voltage source of 100 volts. We have inductor of 870 microhenry. We have a MOSFET. We have a diode. We have a capacitor for smoothing our outputs. It is 2034 microfarad. We have a resistance 10 ohm. It actually doesn't matter that what value you take here, because the main thing is the voltage, and voltage will not depend on the value of this resistor, right? So let's start. So it is 0.06 seconds, which is the normal 3 power frequency cycles. So let's simulate the whole thing, right? So we can see that our pulses are 50% duty cycle, right? So 50% duty cycle, we actually have a particular formula. So the formula goes as Vi, that is V input, upon 1 minus time is equal to V output, right? So right now the time is 0.5 or 50% duty cycle, right? It is 0.5 or 50% duty cycle, right? So what is VI? What is V input? Input is 100 volts. That is divided by 1 minus 0.5. So we will have 100 upon 0.5, which will give us 200 volts, right? So our output, whenever our duty cycle is 50%, should be 200 volts. So let's check. So here we are getting our output as 194, that is almost 200. And here we can see that how this whole thing is reacting. The blue line is the DC voltage that we are applying as an input, and the yellow line is the DC voltage that we are getting as an output. So let's run this for a few more cycles. So we will get a perfect answer. So now we can see that this 100 volt is our DC input, and after some fluctuations our output will be constant. This whole fluctuation will depend on the value of this capacitor. So as we increase or decrease the value of this capacitor, we will get the output. Now let's look the currents, right? So this whole thing is a DC to DC converter, so the current should be DC as well, right? So after some fluctuations we will get the input current and the output current as well. So we need to keep this thing in mind here, that the power in input side and the power in the output side will almost remain constant if we remove all the losses, right? So for that, let's do a calculation. What power means? P is equal to V into I. So we have V as 100 and I here, I we were getting approximately, let's take a display only. So here we have VI input and here we have I output, right? And here let's take a V display here as well. So now we can see we need to multiply 100 into the means V in into I in. So it is 100 into 41.77 and output, that is 19.55 into 195.5, right? So let's see, we are multiplying 100, that is V in into I in, that is 41.77. We will get 4177. And the second thing, that the output, that is 195.5 into 19.55. So here it is 3822. So this is not exactly right. That was the earlier one was 4177 watt and this is 3800 watt, right? So the difference between this is all the fluctuations which is created while we are chopping each and everything. So if we zoom in here, we will see that we are chopping this whole thing. See, it will increase, we will chop. It will increase, we will chop. So the chopping means the frequency of the switching as well as the value of this capacitor will play an important role here. So that's why we are not getting exact answers. But if we run this for a more longer time, so then we can get some desired answers, right? So here now we can see this is our for 50% duty cycle. Let's do for some more. Let's take 0.75, that is 70% of the duty cycle. And if we run this whole thing for 70% duty cycle, we can see the output will go up to 355 volts. See, so it will go up to 355. So from 100 we are getting up to 355 volts. So if we move on to our calculation and put the value here as this value as 75, and what we will get, so here we are putting 0.75, so here it would be 0.75, that is a 75% duty cycle, so it will be 100 upon 0.25, right? So 100 upon 0.25 should give us around 400 volts. So here we can see it is giving 355.7 volts. So it will not reach up to the exact ideal value, because we are not using ideal pulse generator. We are actually generating pulses here. We don't have ideal MOSFET or ideal diode. We don't have the finest and ideal value of capacitor and inductor as well. So it will not reach up to the exact value, but it will go up till the required value. So from 100 volts, it will go to 355 with 0.75 or 75% duty cycle. Let's just take for 25% duty cycle as well. So for 25%, we are getting around 130 or 132, right? So we can say that for 25, we are getting 131, 132. For 50%, we are getting almost double, that is 195 to 200. And for 75% duty cycle, we are getting near about 400 volts in this DC to DC boost converter. So that's it from my side. So if you have any doubt, or if you want to know more about DC to DC boost converters or any other converter in power electronics, please do let me know in the comment section. And if you want, you can also give a feedback, so it would be really helpful to me to make my next videos, right? So thank you so much for watching. Bye.